இப்போ நம்ம அடுத்த செட் ஆஃப் ப்ராப்ளத்துக்குள்ள போறோம். இப்போ நம்ம மைக்கேலுடைய ப்ராப்ளத்தை ஹியர் பண்றதுடைய மிக முக்கியமான நோக்கம் பேசிக் கான்செப்ட்ஸ் புரிஞ்சுக்கிட்டு அந்த கான்செப்ட் எப்படி அப்ளை பண்றோம்ன்ற ஸ்டெப் பை ஸ்டெப்பா தெரிஞ்சுட்டு என்சிஆர்டி ப்ராப்ளத்துக்குள்ள போயிட்டு பிறகு ப்ரீவியஸ் எக்ஸாமினேஷன் கொஸ்டின் பேப்பருடைய ப்ராப்ளத்துல போயிட்டோம்னாக்க நம்ம அந்த சாப்டர்ல தரவாலாம். முதல்ல சாப்டர் தரவா என்சிஆர்டி படி அப்படியே சொல்லித்தரோம். சொல்லி தந்த பிறகு அந்த என்சிஆர்டி சாப்டர்ல இருந்து கான்செப்சுவல் ஏரியா எடுத்துட்டு மைக்கேலுடைய வீடியோ மூலமா ப்ராப்ளம்ஸ் எப்படி வரும்ன்றத சொல்றோம். மைக்கேலுடைய வீடியோ பேஸ் பண்ணி என்சிஆர்டி ப்ராப்ளம்ஸ் நம்ம சால்வ் பண்ணி பார்க்குறோம். சால்வ் பண்ணி பார்த்த பிறகு காம்படிட்டிவ் எக்ஸாமினேஷன்ல வரக்கூடிய கொஸ்டினுக்கு தரவு பண்ணனா we may be going for the examination in a thorough manner actually. அடுத்து போலாமா?
Welcome to our lecture online, and here's another example of how to find the magnetic field near the presence of two current-carrying wires. In this case, though, the two wires are not running parallel to one another. They're running perpendicular to one another. And we're trying to find the magnetic field at this location 10 centimeters away from current-carrying wire 1 and 20 centimeters away from current-carrying wire 2. Again, assuming that the wires are infinitely long relative to the position of this point to the two wires. All right, the best thing to do is to find the direction of the magnetic field at that location due to the two wires. Using your right-hand rule, starting with wire number 1, point your thumb in the direction of the current, and then your fingers will curl in the direction of the magnetic field. Notice that below this wire right here, the magnetic field will be into the board. So using a red color here, so I1 is going to cause a magnetic field into the board right here. We'll call that B1. So again, thumb in the direction of current, the fingers curl in the direction of magnetic field. In front of the wire will be down, below the wire will be into the board. Now, going to this wire right here, current is in this direction. Point your thumb in the direction of the current. Your fingers will curl in the direction of magnetic field. Notice that to the right of this wire right here, the magnetic field will be coming out of the board. So we can indicate that with a point right there. And that would be relative to this wire right there. And so that would be B2. And what we have to do now is find the magnitude of each of those and then add them together. So, magnitude of B1 is equal to, the equation we use is mu sub naught divided by 2 pi times the strength of the current, which would be I1, divided by the distance away from that wire, which would be R1. Notice that R1 right here would be this distance here, so let's call this R1, and this here, that would be called R2. For the second magnetic field, B2, we use the same equation. It's mu sub naught times I2 divided by 2 pi times R2. And now we can go ahead and plug in the numbers and figure out what those are. So this is equal to 4 pi times 10 to the minus 7 Teslas meters per amps, multiplied times the current I1 equal to 8 amps, divided by 2 pi times R1, and R1 in this case would be 10 centimeters, converted to meters is 0.1 meters. Okay, the 4 pi and the 2 pi cancel, this becomes 1, this becomes 2. Using a calculator, what do we get for the first value? So it's 2e to the 7 minus times 8 divided by 0.1. And we get 16, or is it 16 or 1.6? So this is equal to 1.6 times 10 to the minus 5 Teslas. Amps cancel out amps, meters cancel out meters, so you get Teslas. The second magnetic field value here would be 4 pi times 10 to the minus 7 Teslas meters per amps. Multiply this times the current, I2, which is 5 amps, divided by 2 pi, and multiply times the distance, and R2 would be 20 centimeters or 0.2 meters. Again, amps cancel out amps, meters cancel out meters, you end up with Teslas. Let's see how big that is, and again, this cancels out, makes that 2. So 2e to the 7 minus times 5 divided by 0.2 equals, and we get 5 5 times 10 to the minus 6, or 0.5 times 10 to the minus 5 Teslas to keep the same exponential there so we can compare the two. All right, now we want to add them together. Let's say that into the board is negative, out of the board is positive. So the sum of the two, B total, is simply B1 plus B2. And B1 has a value of 1.6 times 10 to the minus 5 Teslas. Now, B1 is into the board, so that's going to be a negative value. So, and that will be in the negative z direction. B2 comes out of the board, that's going to be a positive value, so it's plus 0.5 times 10 to the minus 5 Teslas in the positive z direction. So we sum them together. The total magnetic field caused by those two wires running in different directions is equal to minus 1.6 plus a 0.5. That would be a minus 0.9. Oh, no, not 0.9. That would be a minus 1.1 times 10 to the minus 5 Teslas in the z direction. It's going to be in the negative z direction. So the final magnetic field is going to be into the board with a value of 1.1 times 10 to the minus 5 Tesla.
ரெண்டு வயர்ல கரண்ட் போகுது. 8 ஆம்பியர் கரண்ட் வந்து ஈஸ்ட் வெஸ்ட் டைரக்ஷன்ல போகுது, ஒன்னு நார்த் சவுத் டைரக்ஷன்ல போகுது. ரெண்டு வயரும் ஒன்னு பெர்பெண்டிகுலரா பைசெக்ட் பண்ணிக்குது. ஆனா இங்க என்ன பிரச்சனைனாக்க, ஃபர்ஸ்ட் வயர் 8 ஆம்பியர் கரண்ட்னால 10 சென்டிமீட்டர் இருக்கக்கூடிய ஒரு பாயிண்ட்ல மேக்னெட்டிக் ஃபீல்ட் என்ன அப்படின்னு பாக்குறோம். 20 சென்டிமீட்டர் தொலைவில் 5 ஆம்பியர் கரண்ட் போறதுனால வரக்கூடிய மேக்னெட்டிக் ஃபீல்டு என்ன பார்க்கணும். ஒரு மேக்னெட்டிக் ஃபீல்டு B1 இன்சைட் ஆகும், B2 எமர்ஜிங், என்டரிங் இன் எமர்ஜிங் அவுட்னு ரெண்டு ஃபீல்டு இருக்கு. ஏற்கனவே போட்ட மாதிரி டோட்டல் மேக்னெட்டிக் ஃபீல்டு இஸ் ஈக்குவல் டு B1 பிளஸ் B2. என்டரிங் இன் நெகட்டிவா வச்சுக்கிறோம், எமர்ஜிங் அவுட்டை பாசிட்டிவா வச்சுக்கிறோம். அதுல இருந்து கால்குலேட் பண்றோம். ரொம்ப சிம்பிள் தான். பட் ஆனா இந்த சம் வந்து முதல்ல சார்ஜுக்கு போட்டோம். இப்ப எதுக்கு போடுறோம் அப்படின்னாக்க, ஒரு கரண்ட் கேரிங் இன்ஃபைனைட் கண்டக்டருக்கு போடுறோம். இப்ப மெதுவா நம்ம எங்க போறோம்னா சர்க்குலர் கண்டக்டர் போறோம்.
Welcome to iLectures Online, and here is an interesting example. You're supposed to find the magnetic field at the very center of a current loop. Now this particular current loop is made up of wires coiled up, very tightly bound in a single little bundle. And there's 20 loops all connected together, and a current of 5 amps going through the loops, and the diameter, or at least the radius of this loop, is 10 centimeters. So what's the magnetic field at the center? Well, before we find the magnitude, let's think about the direction. If you curl your thumb in the direction of the current, now you can see how the current goes around the loop, and you put your thumb in the direction of the current, your fingers will curl in the direction of the magnetic field. So there's a magnetic field around this loop. So in the center, it'll into the board, on the outside it'll come out of the board. Doesn't matter what part of the loop you look at. If you look at this part right here where the current is in this direction, you can see again, take your thumb, put in the direction of the current, and the magnetic field will go into the board, inside the loop, and out of the board, outside the loop. So inside the loop, the magnetic field is into the board. All right, now for the magnitude of that. The magnitude of the magnetic field at the center of the loop is equal to mu sub naught divided by 2, then multiplied times the strength of the current, I, multiplied times the number of loops that you have, N, divided by the radius of that loop, R. So plugging in the values, this is equal to 4 pi times 10 to the minus 7 Teslas times meters per amps, multiplied times the current is 5 amps. The number of loops, in this case, is 20, and we divide that by 2 times the radius, which is 10 centimeters, converted to meters is 0.1 meters. Notice that the amps cancel out, the meters cancel out, you're left with Teslas. This 2 will cancel out with that 4, and now we grab the calculator. So we have 2e to the 7 minus times pi times 5 times 20 and divided by 0.1. And the magnetic field at the center has a magnitude of 6.28 times 10 to the minus 4 Teslas. That's the magnitude of the field. And if we want to write it as a vector quantity, since it's into the board, and if we call that the z direction, we could then say that the magnetic field is equal to a negative 6.28 times 10 to the minus 4 Teslas in the z direction. And so we can write.
ஒரு சர்க்குலர் கண்டக்டர்ல 5 ஆம்பியர் கரண்ட் 20 சுற்றுக்களை கொண்ட அந்த சுற்று வழியா போறப்போ அதனுடைய சென்டர்ல ஏற்படக்கூடிய மேக்னெட்டிக் ஃபீல்ட் என்ன? ஏற்கனவே நம்ம இன்ஃபைனைட் கண்டக்டர் கண்டுபிடிச்ச மாதிரி சர்க்குலர் கண்டக்டருக்கு at the center of the coil கால்குலேட் பண்ணியிருக்கோம். μ0I/2r பை மட்டும்தான் வித்தியாசமா இருக்கும். அந்த μ0I/2rல n நம்பர் ஆஃப் டர்ன்ஸ் இருக்கப்ப n ஆட் பண்ணி கால்குலேட் பண்ணிக்கிறோம். என்ன ரொம்ப முக்கியம்னாக்க மேக்னெட்டிக் ஃபீல்டு கண்டுபிடிக்கிறது ரொம்ப முக்கியம்.
Like that. And that's how you find the magnetic field at the center of a set of current loops. Welcome to our lecture online, and here's an example where you're supposed to find the magnetic field inside what we call a coil. Now, a coil is a device that's used in many electronic devices such as computers and video equipment and televisions, you name it. Anything that has any kind of electronics in it typically has coils in it. Even cars have coils in them. So, how do you find the magnetic field caused by a coil? Now, typically when you think about it, you find the direction of the current in the coil around the tube here. So, since the current is going to go this way, behind the tube, out the front, and this way, curl your fingers in the direction of the current around the coil, and the thumb will be in the direction of the magnetic field through the coil like that. So we can see here that we're going to have a magnetic field in this direction. Again, notice that the current goes behind, up, over, and in front like this. So curl your fingers in the direction of the current. Your thumb will be pointing in the direction of the magnetic field inside that coil. Now to find the magnitude of the coil, that can be found by taking mu sub naught, multiplying it times n, and times I. I being the current, mu sub naught, of course, you already know that, and n is representative of the number of loops, or the number of turns as we call it, per unit length. So n is equal to the total number of loops or coils divided by the total length of this coil L. So we can then say that this is equal to mu sub naught times big N over L, big N being the number of turns or number of loops, L being the length of the coil, times the current I. So now go ahead and plug in the numbers. Mu sub naught is equal to 4 pi times 10 to the minus 7 Teslas times meters divided by amps. Multiply it times the total number of loops, which is 400, divided by the length of this, which is 40 centimeters or 0.4 meters. And we multiply that times I, which is 20 amps. Notice that the amps cancel out, the meters cancel out, so we're left with Teslas. And now let's grab a calculator. So we go 4e to the 7 minus times pi times 400 divided by 0.4, and then multiply it times 20. And we got 0.025 Teslas. And so that would be the magnitude of the B field. And of course, if you now want to write in a vector.
இப்போ ஒரு சொலினாய்டு எடுத்துக்கிறோம், ஒரு லீனியர் சொலினாய்டு எடுத்துக்கிறோம். ஒரு காயில் ஒரு ஆக்சில் மேல வைண்ட் அப் ஆயிருக்கு. 40 சென்டிமீட்டர் கொண்ட காயில்ல 400 சுற்றுக்கள் இருக்கு. Ampere circuit law padi magnetic field produced at the center of the coil is defined by the formula mu naught small n into I, where small n is called the number of turns per unit length. Appo capital N by L na போடலாம். mu naught n by L into I substitute பண்ணாக்க நமக்கு ஆன்சர் வந்திருக்கு.
Quantity, since you know that it's to the right, so that's the positive x direction. In this case, you could say that the magnetic field B inside the coil is equal to a positive 0.025 Teslas in the x direction. Now, what's the magnetic field outside the coil? Well, outside the coil, the magnetic field will loop back and make a complete circle, so the magnetic field will come back this way, go back in here, and like that. So you have additional magnetic field coming out this way, and back in, and this way and back in. So you can see that the magnetic field strength outside the coil is very weak, but the magnetic field inside the coil is very strong. All right, and that's how you find the magnetic field inside a coil. Welcome to iLecture Online, and here's another example of how we work with forces and magnetic fields. In this case, we have two parallel conductors, and we're trying to find the force between those two parallel conductors. So one has a current of 4 amps going upward, the other one has a current of 8 amps going downward, and they are 2 meters apart. So why would there be any forces between them? Well, it turns out that each of these conductors will have a magnetic field around them, and that the conductor, let's say conductor number 2, is in the presence of the magnetic field caused by conductor number 1, so therefore it will feel a force, and conductor number 1 is in the presence of the field of conductor number 2, so it will feel a force. So the strategy here is to find out first what the magnetic field strength is and direction over here caused by this conductor, and then we find out what the magnetic field strength is over here caused by that conductor. So let's do that. Well, first we're going to find the direction of the magnetic field, and using our right hand rule, we put our thumb in the direction of the current, our fingers curl in the direction of magnetic field, so the magnetic field is in a circular direction around this conductor right here, which means to the right it is into the board, and so I'm using blue to indicate that that belongs to this conductor, and of course on the left side of the conductor it is out of the board, so I'll represent that with dots. So there's a magnetic field, I'll call it B sub 1, caused by conductor 1. Which means that conductor 2 now is inside this field, and it will feel a force based upon the direction and the magnitude of this B field and the current in wire number 2. Now, conductor number 2 is going to have a magnetic field over here. Using our right hand rule, we direct our thumb in the direction of the current, our fingers curl in the direction of the magnetic field, so it'll come out of the board here and into the board on that side. Let me use a red pen to indicate the B field caused by this conductor. So again, current going this way, B field into the board to the left, so here we'll have a B field into the board caused by conductor number 2. And of course this B field is everywhere on this side, but on this side it'll be coming out of the board, so I'll indicate that with dots. So over here where conductor number 1 is, we have B field caused by conductor number 2, and I'll call that B sub 2. Now we have to find out the magnitude of each of these magnetic fields. So B number 1, or B field number 1, has a magnitude equal to, I'm going to use the equation, mu sub naught divided by 2 pi times the current divided by the distance away from the conductor that causes the B field. All right, so current here is I1, so we'll call it I1, and we'll call that R1. Of course, R will be the same for both. And plugging in the numbers, this is equal to 4 pi times 10 to the minus 7. That's Teslas meters per amps. We multiply that times the current, and the current there will be 4 amps. And then we divide that by 2 pi times the distance, and the distance will be 2 meters. So it'll be 2 meters like that. All right. Simplifying this a little bit before we grab our calculator, we see a 4 pi over there. We see a 2 pi times 2, which is also 4 pi, so that cancels out. So that means at the top we have 4, of course meters cancels out meters, amp cancels out amps, so we have 4 times 10 to the minus 7 Teslas. So that's the strength of the magnetic field over here where conductor 2 is, caused by conductor number 1. Now we find the magnetic field strength of B2 caused by conductor 2, so we have B2 is equal to mu sub naught divided by 2 pi times I2 over R2. Of course R1 and R2 in this case are the same. Plugging in the numbers, we get 4 pi times 10 to the minus 7 Teslas meters per amps. We multiply that times 8 amps. Now you say, well, shouldn't we have a negative and positive current depending upon which direction it goes? Not really. We're simply finding the magnitude, and of course I should put magnitude signs on here. We're simply finding the magnitude, the direction is already decided by using our right hand rule. We divide that by 2 pi and the distance r, which is 2 meters. And again, these 4 pi cancels out those 4 pi. Looks like I picked the right numbers in this case. The amps cancel out, the meters cancel out, and so we're left with 8 times 10 to the minus 7 Teslas. All right. So that means the strength of the B field over here where conductor 1 is 8 times 10 to the minus 7 Teslas. And the B field over here, the strength of the B field over here is 4 times 10 to the minus 7 Teslas. Now we need to find the force on each of these conductors. And not only the force, we also need to find the direction of the force. So let me find a different color here. And let's see here. Conductor number 2 is inside the B field of conductor number 1. If I take my right-hand rule and I point my fingers in the direction of the current, so I'll stand over here. So the current is coming down this way, and the B field number 1 curls inward to the board, so it has a force outward like this. So the force on conductor number 2 is to the outside. So let's call that force number 2. So that's the force on conductor 2 caused by the magnetic field of conductor 1. Now, coming over here, use my right-hand rule, I point my fingers in the direction of the current, and it's under the influence of the B field from conductor 2. Those are the red crosses here, so I go up, point my fingers inward towards the B field, my thumb points out towards this way, so the force on conductor number 1 will be to the left. And so we'll call that force 2. Not force 2, we'll call that force 1, the force on conductor 1 caused by the big magnetic field from conductor 2. All right, now we need to know what the force is, what the magnitude of the forces are equal to. So let's start with force number 1. The magnitude is equal to, and if we remember the equation to find the force on a conductor in a magnetic field is equal to, let's see here, it's equal to I, and that would be the current in 1, times the B field caused by conductor number 2, so we'll call that B2, times the length of the wire that's underneath the influence of that magnetic field. Now, we haven't indicated yet how long a wire is under influence, so let's say that the wires have a length equal to 3 meters. So we'll call that a 3-meter long wire. All right, plugging in the numbers. The current, well, before we actually do that, what is B2 equal to? Well, B2 is right here, comes from there, so we do have everything we need. So I1 is 4 amps. B2 is 8 times 10 to the minus 7 Teslas. And then the length of the wire we said was 3 meters. And that will give us, let's see, 4 times 8 is 32, times 3 is 96. That would be 96 times 10 to the minus 7. Units are Teslas, meters times amps, and that would then be 96 times 10 to the minus 7 newtons. All right. Now, for the force on the other wire, force on the second conductor, that's equal to I in the second conductor times the B field that it's being subjected to, which is the B field from conductor 1, times the length of the wire that's being subjected to the B field. And so that's going to be equal to, I2 is 8 amps in this case. The magnetic field B1 is 4 times 10 to the minus 7 Teslas, and then it's also a 3-meter long wire, and so that will be also 96 times 10 to the minus 7 Teslas, meters times amps, which is 96 times 10 to the minus 7 newtons. And so those are the forces on the two conductors due to the magnetic fields that are subjected to one another. All right, that's how you do a problem like that.
இப்போ ரெண்டு parallel wire எடுத்துக்கலாம். ஒண்ணுல 4 ampere, இன்னொன்னுல 8 ampere. கரண்ட் டைரக்ஷன் சேஞ்ச் ஆகுது. ஒண்ணுனால இன்னொன்னுல என்ன ஃபீல்ட் ஏற்படுது, அதனால என்ன ஃபோர்ஸ் ஏற்படுதுன்னு பார்த்தோம். நம்ம ரெண்டு parallel wireலயும் கரண்ட் போறப்போ வரக்கூடிய ஃபோர்ஸுக்கான டெரிவேஷன் மெத்தட்லயே ப்ராப்ளத்தை சால்வ் பண்ணிருக்கோம்.
Welcome to our lectures online, and here we're going to talk about Ampere's law. That's an interesting name, is Ampere. It's a French physicist who figured out the relationship between currents and Ohm's law and so forth, and therefore we named the unit of current after him, amps. So what is Ampere's law? Well, he discovered that if we had, for example, a set of currents in a particular area, let's say 3 conductors side by side, then they each carried a certain amount of current, I1, I2, and I3, And if we drew an imaginary circle around those three currents, what he said was that if we figure out the strength of the magnetic field anywhere along this imaginary line, so for example over here the B field might be kind of like this in that particular area of the curve, and then if we took a small little line segment along this and we call that a small little DL, and of course that means there was a small little angle between them. What he said was if we multiply these two together, for example, if we went B dot DL, which of course, if we want to calculate that, that is equal to the strength of the B field times the length of the little line segment times the cosine of the angle between them, like that. And if we did that for every little line segment all the way around the circle like that, and we added all those products up, so we did that time and time again, we found the B field in each particular case, so the B field there would be maybe like this, and like this, and like this. Sometimes the B field would be parallel to each other, or parallel to the line segment DL. If we added up all those products, B dot DL, he figured out, for example, if we sum them all up, and of course summation is an integral sign, if we summed up all the B dot DLs all the way around the circle, he said that was always equal to the I enclosed multiplied times mu sub naught. And that becomes a very interesting equation. Now, in a case like this, where you have multiple current conductors in there, having different currents, maybe pointing in different directions, that would be kind of a difficult problem to solve. But if it's very symmetric, for example, if we have a single conductor in there, to the example, if we have a single conductor, let's say that I is equal to 5 amps, and we drew a circle around it like this, and we put the conductor right in the very center of that circle, then we know that the B field will be uniform anywhere along that circle. The B field, of course, if you use a right-hand rule, if we point the thumb in the direction of the current, let's say the current is upward like this, then we could see that the B field would be perpendicular to that. So everywhere along the curve, the B field would be exactly perpendicular to that imaginary circle, like so, like so, like so, like so. And since the B field doesn't change, only changes in direction, but it doesn't change in magnitude anywhere along the field, and we can also see that the direction of the B field is always parallel to the direction of the little line segment that we could potentially place there in each case. So we have a little DL there, we have a little DL there, we have a little DL there. In each case, the B field is parallel to the line segment. Then this becomes a very practical equation. Because let's say that we make that circle with radius r, and we want to find out what the B field is along that line. Let's use what we call Ampere's law to do that. So we take the integral of B dot DL, and we say that's equal to mu sub naught times I enclosed. Now, since we know that in each case, the B field direction and the line segment direction will be parallel, and of course B dot DL means B times DL times the cosine of the angle between them, and if the angle between them is 0, the cosine of 0 is 1, right? This then becomes 1, then it's simply the integral of the B field. Oh, and then we don't have to put the vector notation on there. We can simply say it's B field times DL equals mu initial, or mu sub naught times I enclosed. Okay, so now, since the B field magnitude doesn't change anywhere along that circle, we can take the outside integral sign, so we can write B times the integral of DL all the way around the circle is equal to mu sub naught times I enclosed. And then, of course, when we take the integral all the way around the circle, since it's a circle, the integral of a DL all the way around the circle is simply the circumference of the circle, so we can say that that's equal to B times 2 pi r equals mu sub naught times I enclosed. And then finally, if we then isolate this equation for B, we get B is equal to mu sub naught divided by 2 pi times I enclosed divided by the radius of the circle. And this then becomes the equation you're already familiar with. That is the equation of a B field anywhere outside a current carrying conductor. If the current carrying conductor has current I running through it,
ஆம்பியர் சர்க்யூட்டல் லா அப்படின்ற ஒரு லாவை மெதுவாக எக்ஸ்பிளைன் பண்ண ஆரம்பிக்கிறாங்க. இப்போ என்ன செய்யறோம்னாக்க ஒரு இன்ஃபைனைட் கண்டக்டர்ல கரண்ட் போச்சுன்னா சுற்றி இருக்கக்கூடிய ஒரு பாயிண்ட்ல மேக்னெட்டிக் ஃபீல்டுக்கான ஃபார்முலா தெரியும். If r is the distance of the point of observation, mu naught 2 pi I by r அப்படின்ற ஃபார்முலா நமக்கு தெரியும். இப்போ Bன்றது ஃபீல்ட் ஆஃப் இண்டக்ஷனா இருந்து dlன்றது அந்த இன்ஃபினிட்டிசிபிள் கரண்ட் எலிமெண்டா இருந்ததுன்னா ஐன்ற கரண்ட் அந்த கரண்ட் எலிமெண்ட் வழியா போறப்போ b டாட் dl உடைய க்ளோஸ் இன்டெக்ரல்ல தான் வேல்யூ வந்து mu naught into I enclosed ஈக்குவலா இருக்கும்னு சொல்லிட்டு ஆம்பியருடைய சர்க்யூட் லாவினுடைய கான்செப்ட் எடுத்துட்டு ப்ரூவ் பண்ணிருக்காங்க.
And your distance r away from the conductor. So you can see that this can be a very practical way of solving problems. So in the next example, I'm going to do something a little bit more complicated, but again, using Ampere's law here, we're going to be able to solve that rather easily. Welcome to our lecture online, and here's an example of how to use Ampere's law on a problem. So let's read the problem. It says, find the magnetic field 1 millimeter from the center of a current-carrying conductor that is 6 millimeters in diameter. So you're right inside the conductor if it has a current of 50 amps. And then it asks, what is the magnetic field 30 centimeters from the center? And that means that now you're outside the conductor. So what is the magnetic field inside the conductor, and what's the magnetic field outside the conductor? Okay, so let's make a drawing of that. So here's our conductor. We blow it up so I can see the fine detail. Let's say it has a current I equals to 50 amps. And imagine then that the current flows throughout the conductor evenly everywhere. So you can imagine something like this, where current is flowing everywhere through the conductor, the edges, the inside, all throughout. And let's say that's uniformly distributed. So now what we're going to do is we're going to realize that the radius of the conductor is equal to 6 millimeters. Nope, that's the diameter, so the radius is half of that, so the radius is 3 millimeters. And we're concerned, or we're not concerned, but we're interested, that's a better way to put it, to find out what the magnetic field is 1 millimeter away from the center. So let's make that small r equals 1 millimeter, and we want to know what the magnetic field is at that particular location. So imagine then that we have a Gaussian, not a Gaussian surface, but an Ampere circle around that center where the radius is 1 millimeter. And using Ampere's law, we can say that the line integral of B dot dl is equal to mu sub naught times the current enclosed by that circle. And of course, here in this case, the circle has a radius of 1 millimeter because we want to put the edge of that circle right at the point where we want to know what the magnetic field is. Since it's nicely symmetric, we know then that the B field will be parallel to the circle anywhere along the point of the circle. So that means that B will be constant at that point. We can then take B outside the integral sign. We can write that B times the integral of dl. And of course, since B and dl will be parallel, the cosine of the angle between them, which is then 0 degrees, is 1. We can simply write it like that. And this is then the line integral of the integral going all the way around the little circle. That's equal to mu sub naught times I enclosed. So the next thing we do is find out what this integral is. It's simply the circumference of that little circle, the radius is little r, so we can write then that b times 2 pi times little r is equal to mu initial, or mu sub naught times I enclosed. Now the last thing we need to do here is find out how much current is flowing through that little portion of that conductor. So it's going to be the total current going through the entire conductor times the ratio of the cross-sectional area of the little circle divided by the cross-sectional area of the entire conductor. So I enclosed is equal to the current flowing through the whole wire times the ratio of the cross-sectional area of that small little conductor, which is pi times little r squared, divided by the cross-sectional area of the entire conductor, which is pi times big R squared. And so pi's cancel out, and it's simply I times the ratio of little r squared divided by big R squared. And that we can put in there. So we can say that B times 2 pi times little r is equal to mu initial times total current times little r squared divided by big R squared. Then we can see that this r can cancel out one of those, and then we can divide both sides by 2 pi, so we get b is equal to mu sub naught divided by 2 pi times I times the ratio of little r over big R squared. And now we're ready to go ahead and plug in some numbers to see what that is equal to. So this is equal to mu sub naught, which is 4 pi times 10 to the minus 7. That'd be Teslas meters per amps. We multiply that times the current. We said the current was 50 amps. We then multiply times the radius of the little circle, and that would be 1 millimeter, which is 1 times 10 to the minus 3 meters. Then we divide that by 2 pi. And then we divide that by the radius of the conductor squared. It's a 3 millimeter radius, so that's 3 millimeters, or 3 times 10 to the minus 3 quantity, and that would be meters, and that would be squared. All right, now we need a calculator, and I have one handy here in my pocket. Before we use it, we can see that this pi cancels out this pi, and this 4 becomes a 2, that becomes a 1, and now we're ready to go. So we have 2 e to the 7 minus times 50 times 0.001 equals, now we divide that by 3 times 10 to the minus 3 squared, that's 6 times 10 to the minus 6, so divided by, that would be divided by 6 e to the 6 minus equals, and it looks like we have a B field strength of 1.67 times 10 to the minus 3 Teslas, because meters cancels out meters, and this cancels out the second one, and then amps cancels out amps like that. So we end up with 1.67 times 10 to the minus 3 Teslas. Now that's the magnetic field inside the conductor, 1 millimeter away from the center of the conductor. Does that mean that the field will get stronger as I go further and further out? And the answer is yes. Remember that the B field is a function of the radius of where we're at inside a conductor. That will then continue, and as this gets bigger, the B field will get bigger as you go further and further out. And it looks
ஒரு கண்டக்டர் வந்து ஒரு குறிப்பிட்ட ரேடியஸ் இருக்கக்கூடிய சிலிண்ட்ரிக்கல் வடிவத்துல இருந்து அதனுடைய சென்டர்ல இருந்து 1 மில்லிமீட்டர் ரேடியஸ் இருக்கக்கூடிய ஒரு ஏரியால எவ்வளவு மேக்னெட்டிக் ஃபீல்ட் இருக்கணும்னாக்கா ஆம்பியர் செக்யூட் லாவை யூஸ் பண்றோம். இங்க பியூட்டி என்னன்னாக்கா மொத்த கரண்ட் யூனிஃபார்மா பாயறப்போ அது வழியா பாயக்கூடிய கரண்ட்டுடைய ரேஷியோ கண்டுபிடிச்சார். இப்போ அந்த I ஸ்மால் ஆர் ஸ்கொயர் பை கேபிட்டல் ஆர் ஸ்கொயர் தான் அங்க பியூட்டி. சப்ஸ்டிடியூட் பண்ணி வேல்யூ கால்குலேட் பண்ணியிருக்கோம். மற்றபடி எல்லாமே ஒன்றும் பிரச்சனை இல்லை. B dot dl is equal to mu naught into I enclosed. இந்த I enclosed கண்டுபிடிக்கிறது. ஏன்னா dl is equal to 2 pi r உங்களுக்கு தெரியும். B into 2 pi r is equal to mu naught into I enclosed. I enclosedல மொத்த கரண்ட்ல எவ்வளவு கரண்ட் எவ்வளவு ப்ரொபோர்ஷனேட் கரண்ட் அது வழியா போகும். மொத்த கரண்ட் கேபிட்டல் ஆர் வழியா போகுது. ஸ்மால் ஆர் வழியா போகக்கூடிய கரண்ட்டை I into pi r square by pi capital R square போட்டு கால்குலேட் பண்ணி போட்டிருக்காரு. It's a wonderful way of doing it.
Like it's a linear relationship. The B field is proportional to the radius to the first power, so where you're inside the conductor. Now the next part is we need to find the magnetic field outside the conductor. So now we draw a new circle around the conductor. Now we're the radius here. Let's call that radius sub 2. The second radius is equal to 30 centimeters. And now we do the whole thing over again. We go through the same process. We know that the, I shouldn't call it a big R because that makes it confusing. Let's make it a small r, just like we did before, but I'm going to call it R sub 2. So we're going to have the same equation like we did before, the same condition, same equation. And so now we'll end up with B times 2 pi R sub 2, because now we're dealing with a much larger radius circle that goes well beyond the conductor, is equal to mu sub naught times I enclosed. And now you can see that in this case, the I enclosed is going to be all of the current through the conductor, because the entire conductor is circumvented by your ampere circle. So that means for I enclosed, in this case, it will be the entire 50 amps, and R2 is simply the distance out to where we want to know the magnetic field. So we can then write this as B is equal to mu sub naught times 50 amps divided by 2 pi times the radius of the circle. That means the radius out to the point where we want to know the magnetic field strength. Plugging in the numbers, this would be equal to mu sub naught is 4 pi times 10 to the minus 7 Teslas meters per amps. We multiply that times 50 amps, and then we divide that here by 2 pi times the radius. In this case, the radius is 0.3 meters. And again, the units cancel out, becomes Teslas. This 4 pi cancel out with this 2 pi, this will be 1, this will be 2. And I'm plugging the numbers in this case. What do we get? So we have 2 E7 minus times 50, and we divide that by 0.3. And it looks like the magnetic field strength there, the B field in this case is going to be 3.33 times 10 to the minus 5 Teslas. So that's the magnetic field strength way out here, 30 centimeters from the center of the conductor. Here, this was the magnetic field strength inside the conductor, just 1 millimeter away from the center. Now, what about the direction? Well, we use our right-hand rule. Current is directed upward, so the magnetic field will be in a direction this way around the conductor. So if we use a red color to indicate the magnetic field direction, so here the B field will be in this direction, here the B field will be in this direction, here the B field will be in this direction, and here the B field will be in this direction. So it's going to go around like that, counterclockwise, looking from the top. And of course, for the outside B field, it'll be the same. Again, we use the right-hand rule. B field will be directed around like this, so the B field will be outward like this in all directions, B field, and coming here, that'll be the B field, and down here, the B field is in this direction. So for the outside circle, we have this as a result, and then for the inside circle, we have this as the magnitude of the B field. And that's how you can use Ampere's law to find the B field inside conductors as well.
Ampere circuitral law vache inside the conductor circumference la uniform current flow ஆறப்போ value calculate பண்ணிரு. தொடர்ந்து பார்க்கலாம். அதுக்கு முன்னாடி ரெண்டு law வந்து பிரம்மாண்டமா யூஸ் ஆகுது. Biot-Savart's lawவும் Ampere lawவும். இந்த கான்செப்சுவல் ப்ராப்ளம் தெரியாம நம்ம நேரடியா ஃபார்முலா யூஸ் பண்ண ஆரம்பிச்சோம்னாக்க நமக்கு நிறைய புரியாம போயிடும். We'll continue with it.